It's a pleasure to be with you this morning or afternoon. And I'm going to give a talk about some work that we've been doing. It's on mixed precision in numerical computations. And in particular, we're going to look at some linear algebra things. So this work actually began with my PhD dissertation. So this is a work that took place in the 1980s. I think I got my degree in 1980, and the title of my dissertation is given there. It's Improving the Accuracy of Computed Matrix Eigenvalues. And the idea was to compute eigenvalues and eigenvectors in lower precision and then selectively improve their accuracy. And you could do that using the techniques that I developed for order n squared operations. So you do the complete eigenvalue computation, order n cubed in lower precision, and then you selectively enhance the accuracy of those lower precision values up to higher precision. Let's say single precision was the original thing, and then double precision was the ultimate thing, the higher precision results. And the going from single to double precision only cost you order n squared operations. And the ideas were extended to singular values. There was a paper that appeared in SIAM Journal of Numerical Analysis with myself, my advisor, and Jim Wilkinson as well. And there's an algorithm that appears in ACM Toms that describes that in great detail. So let's move on to the next slide. Back in 2004, there was a processor that IBM came out with called the cell processor. And the cell processor was sort of interesting. It was used for a PlayStation, so it was used to drive games. It had a very high performance graphics processor. And that graphics processor could do 32-bit floating point arithmetic. It was IEEE arithmetic. It did 32-bit floating point arithmetic at a speed of around, let's say, 200 gigaflops. And if you looked at 64-bit arithmetic, it ran only at 14 gigaflops. So it was a great difference between the single and double precision. And the result of that drove us to look at algorithms where we can exploit that single precision result, trying to capture that 200 gigaflop performance, and then selectively enhance the value of whatever we were computing, paying the price of the 14 gigaflops. So you want to do the bulk of the computation in the single precision, and then selectively enhance the value in double precision. So that was a great tool. It helped us in terms of looking at ideas and exploring things and moving forward. So again, the idea is to exploit the 32-bit arithmetic as much as possible, do the bulk of the work in that precision, and then correct or update the solution selectively with 64-bit arithmetic. Do the computation, calculate a correction to the 32-bit results, and then enhance that value, and then carry on with that. So there's an algorithm that we used. The algorithm is this was done on the cell processor. So this is back in 2000, early 2000, which used lower precision. LU decomposition takes n cubed operations. And the idea was to do that n cubed operation part in 32-bit arithmetic, and then iterate to get higher precision using n squared operations. So the idea was to, again, bulk of the computation in lower precision, and then selectively use the 64-bit to do the correction. And with this process, you could do the correction in order n squared operations. So the algorithm that we used was iterative refinement. Iterative refinement says compute a solution to AX equals B, factor a matrix, compute the solution, and then compute a residual. So the residual is computed, so it's B minus AX. So I need a copy of the original matrix. So this is a penalty, I'll say, of the method. I need to keep a copy of the original data in 64 bits. I need a copy of the data in 32 bits, which I use to factor. So the LU factorization consumes the 32-bit matrix version. and L and U overwrite the matrix in 32 bits. And then the residual is computed with that original copy in 64 bits. So the residual is computed in 64-bit arithmetic. LU is in 32. The solution X is computed in 32. And then using that 64-bit residual, we go into an iterative process. And the iterative process says we're going to compute a correction. That correction is called, let's call it Z. So Z, the correction, comes from solving the equation AZ equals R. And there's a bit of mathematics which I can't go into, but that correction Z is actually the correction to the solution. So there's some mathematics which goes on behind the scenes to make that whole, make that correct, so that that vector Z that we're computing is really a correction to the solution X. And we update that in higher precision, so that new value of X is in higher precision. And then we compute a residual and we iterate. And again, that's an algorithm which is well understood. It's discussed for many years. We added the twist of doing the 32 and 64-bit. This was used originally in a way to enhance the solution, and we can get by. So the penalty here is that you have to have a copy of the original data in 64-bit and a copy in 32-bit. So it's a penalty, I'll say, of having 1.5 times the storage. And the other issue is the matrix can't be too badly conditioned. If the matrix is too badly conditioned, then we're not going to be able to enhance the solution. But if I can get 1 digit correct in 32-bit arithmetic, the method will converge. And the method is actually similar to Newton's method. So if I have a good approximation to the solution, I'm going to get sort of quadratic convergence here. So this is something which is going to converge very quickly if the matrix is well conditioned. If the matrix is badly conditioned, it'll tamp that down and slow the convergence down. So if I only get 1 digit right, it'll probably give me only 1 additional digit per iteration, but I will in fact converge to a 64-bit accurate solution. So there were some papers that were published that discussed this in gory detail. And again, the driving impetus here was for using that hardware that we had from the Sony PlayStation, the cell processor. And just to give you a sense here, this is the performance that we see for matrix multiply. So this is just looking at that difference between the 32-bit and the 64-bit performance. So for doing matrix multiply, the theoretical performance is given there in the dark blue and the turquoise line for double precision. So you can see that large difference there. And if you run matrix multiply in single precision, you come close to that theoretical peak performance. So I think we're getting around 180 gigaflops in this particular implementation of our thing. And if you do factorization, so this is doing the LU factorization. The purple one is doing everything in double precision, and the lighter pink one is in single precision. So you can see the difference there, that large gap between the performance. So we haven't done any improvements to the solution here. We're getting just single or double precision results in that kind of performance. And if you do the iterative refinement, doing this mixed precision thing, we come in with a solution which is as accurate as the double precision result, but gives you a solution which is a lot faster. And so we get a speed up here of around 8 over what we would have done had we done the computation originally in double precision. So there was a great excitement about this, and a lot of work was done around the idea. And this was again in the early around 2004, 2005, and then the results were interesting. They found their way into LAPAC. So this algorithm, mixed precision, found its way into LAPAC. And if you had that great difference in performance, you would see great improvements in your performance. If you didn't, and typically single and double precision is usually a factor of 2, not a factor of 8 or 10. But even with the factor of 2, we see an improvement in performance with this on what I'll call conventional architectures. And so it's an intriguing potential here of exploiting this lower precision as much as possible, and then switching, let's say, somewhere in the computation to exploit double precision. And we looked at using these ideas for iterative methods for solving systems of equations. So we're going to start the iteration in a lower precision and get an approximation, and then switch to a higher precision later. So we are getting some benefit of that single precision results. So there's great potential here. GPUs, FPGAs is another thing. There was some experiments done with FPGAs where you can basically dial up how much accuracy you're going to get in your floating point arithmetic. And I saw a paper which exploited that for that problem. So linear systems and eigenvalues, it was easy to do. The problem is the basic thing we're doing is Newton's method. So Newton's method says we're going to solve this equation here. The new solution is equal to the old solution minus the function evaluated at the old solution over the derivative of the function. And we're going to rephrase that slightly. We're not going to compute the new solution. We're going to compute a correction to the solution. So this is an important aspect. We're computing not the solution, but a correction. So the bits at the low end are being computed, not the bits at the high end. So we're really refining things at the low end. And that allows us to enhance the solution then by adding those low end bits to the approximation that we have. And you can think of it in some sense in this way. We have a value xi, and we're going to compute this correction, this value z, which is going to enhance it, and it enhances those low order bits so that the new solution, xi plus 1, has a larger number of bits which are correct in that way. And then we're going to use that xi plus 1 in the next iteration, which is going to be done again in short precision. So we truncate it there, we do the computation, and we compute a correction again to it. Ultimately, it's going to converge to the solution that we would have gotten had we done the whole computation in the higher precision. And again, there's those caveats about the conditioning of the problem has to be good enough to allow this to happen. Well, along comes machine learning, and machine learning is being used in many fields. It's a very very powerful tool, I'll say, for use in many things. And we're finding that climate modeling, biology, drug design, materials, high energy physics, all are looking at using some aspects of machine learning and enhancing their solution. So machine learning is going to be a tool that computational scientists use going forward. And the interesting thing about machine learning is that it's based at the core of what we're doing is small matrix multiplies. So we have this neural network, and we're going to be using small matrix multiplies in that neural network to do these convolution deconvolution steps to enhance the classification. And those can be done in lower precision, so they don't require higher precision. So machine learning can be driven by lower precision, and the architects understand that 16-bit arithmetic can be exploited, and it drives manufacturers then to produce hardware which exploits that. So today we have machines which can do 16-bit floating point arithmetic. There's a standard that defines these things. 16-bit floating point arithmetic and IEEE says there are 16 bits. It has a range of 10 to the 5. So the largest number you can exploit is 10 to the 5. So a number above 65,000 will cause overflow. So this is an issue, and it's going to require some handling of the problem, some scaling to get it correct. And in single precision, the results are as accurate to roughly 10 to the 5, 10 to the minus 5, or 10 to the minus 4 in that range there. That's the precision that we're going to have. And again, the important thing is the exponent only allows for the largest number to be 65,000. That's the IEEE version of this. A number of people said, well, that's pretty restrictive. They're going to look at a different implementation. So this is not IEEE. This is something called bfloat 16. It was, I guess, promoted by Google in its tensor cores. and it has a slightly different representation of that number. So they gain more exponents. So instead of 5 bits for the exponent, they increase that to 8 bits, and at the cost of the fraction. So instead of the accuracy being 10 bits, it reduces it down to 7 bits. So the impact of that is that the largest number now is 10 to the 38, which, by the way, is the same thing as single precision. So if you take a look at the single precision IEEE specification, it's basically the same exponent range as B float 16, but of course the fraction part has been truncated to have only 7 bits instead of 32 bits. So that's those are the two standards, and that's causing some confusion and some issues. Which one is better? So one has a bit more accuracy, and the other has a bit more dynamic range to the numbers. And if you use float 16, then you have to be careful about doing scaling. You can do it, but your numbers can't be greater than 65,000. Otherwise, you'll overflow. So there are some issues there about underflow and overflow issues if you do the scaling, and that causes some problems for some algorithms. But it can be done, and people have done it, and there's been papers written about how you can do that and what the best way of doing that is. So today we have these precisions. Half precision is increasingly supported in hardware. It's being driven by machine learning. NVIDIA has it in Pascal and Volta and Ampere. They use bfloat. Some of the other vendors use bfloat 16. So some vendors use float 16 and some use bfloat 16. And you can see there are some of the ones that have half precision implemented in hardware. And notable, the one at the end there, the Fujitsu, the ARM processor that's being used in the fastest computer, Fugaku, in Japan, that uses floating point 16, the IEEE representation. So they do not do bfloat, they do float 16. And but they do have it, and it runs very efficiently on their architecture. I'll mention that more in a moment. So if we take a look at NVIDIA, which is perhaps the most popular GPU that's being used for scientific computing today, what we see really are 4 performance levels from the hardware. So there's 64-bit floating point arithmetic, and that's accomplished through an FMA instruction, and that achieves a peak performance of 7.5 teraflops. So the hardware permits something which is in 64-bit accuracy up to 7.5. If you go to 32-bit floating point arithmetic, again using an FMA-like instruction, in the hardware it's 15, so it doubles the performance. And if you go down to 16-bit floating point, you can also do an FMA instruction, and that gives you, again, a doubling, so you get 30 teraflops. But the Volta has this special hardware which does tensor cores. It does a 4x4 matrix multiply, again, being driven by the machine learning folks, which is capable of doing that 4x4 matrix multiply at 120 teraflops. So if you have a problem which is matrix multiply that can exploit 16-bit arithmetic, you can see a tremendous enhancement in performance. So that's the great advantage of doing that, that's led to a number of interesting results. And the Volta, the way it does its matrix multiply, it's giving you more accuracy than you deserve in some sense. So the input is 16 bits. It does the multiply to full 32-bit accuracy. It then does the accumulations that are done in the matrix multiply to 32-bit accuracy, and produces a 32-bit accurate results, which are then truncated for the storing of the final product. So again, the inputs to this are 4x4 matrices, and the output is a 4x4 matrix ultimately. And that 4x4 matrix then is truncated to 16 bits, and then you can repeat the process. But internally, you're getting 32-bit accuracy for this matrix multiply. So in some sense, you got more accuracy than you deserve out of that matrix multiply, which helps the problem. So if we look at the Volta and we look at half precision, this is 64 bits result. So this is matrix multiply. I've got square matrices. This is what I see if I run an experiment changing the order of the matrix. I see something which is around 6.4 teraflops for matrix multiply. If I went to single precision, 32-bit results, again for matrix multiply, this is not mixed precision now, this is just doing matrix multiply. I end up with a factor of 2. If I use the 16-bit using the FMA instruction, so not using the tensor core, not doing 4x4 matrix multiplies internally, just using the FMA instruction, I get a doubling again in performance. But if I do use the tensor core, I see this big improvement. And now I'm splitting up the larger matrix multiply into 4x4 blocks, which are done on the tensor core. And in this case here, I'm achieving at best 85 teraflops. So you see the big improvement in performance that can be exploited if you use that special hardware that's on that machine. And we want to use that in our linear algebra computations if we can. I'll say that this is for square matrices. So these are for large square matrices. And for the linear algebra stuff that we do, we don't have square matrices. We have basically a rank K update to a matrix, which we call a matrix multiply. It's a rank K update to a matrix. It's a sure complement that we're computing, and it has this form. And when we use this form on that tensor core, on that NVIDIA product, we see a drop in performance. And that drop comes from more data movement. And I don't have time to explain all the details of this, but it's a significant drop in performance. We lose roughly a factor of 2 in the 16-bit tensor core product because of that data movement issue. And there's no way around that. So if I have a sure complement, a rank K update to a matrix, I'm not going to see quite the high performance, but I will see some improvement in performance. So I just want to stress that in the best case, it looks great. In the practical case, it's not quite as great as it might seem. And that's a reality that's caused by data movement of those blocks. So if I think about factoring a matrix now, and this is not in doing any iterative improvement, this is just factoring a matrix. What I'm showing here is double precision, single precision, then using the tensor core. So we see that bump if you can exploit 16-bit arithmetic and be happy with 16-bit arithmetic, you get a factor of 4 over the 64-bit results. And this is for doing LU factorization. So this is using that tensor core to do that factorization, getting slightly better performance than we should. But again, this is just doing, the result is a 16-bit accurate solution. So this is the best that we can do in that case. Now we want to go ahead and do this mixed precision thing. And we've written a few papers about this, looking at how we do this. It does a few things. It computes the time to solution faster. And a byproduct of that is that we consume less energy. So the power reduction is coming because we're reducing the execution time. That's really where that power reduction comes. And I'll show you that again very precisely. And again, we're reformulating the solution. We're going to reformulate the solution here to computer correction rather than the solution itself. And there's been a bunch of papers that have talked about that. Okay, so here's the algorithm that we're going to look at. Again, it's this iterative refinement thing. We're going to factor a matrix. We're going to use lower precision to factor the matrix. We're going to compute a residual in higher precision. And then we're going to go through this iterative process to compute a correction, add the correction to the solution, and then compute a new residual and carry on. And we selectively use that 64-bit results, initially computing the factorization in the lower precision. Okay, so the classical iterative refinement says to compute that correction by using the factors that we have, the LU factors with the residual. That's the classic solution to that problem. That's the Wilkinson solution to iterative refinement. More recently, Nick Hyam and Aaron Carson said, well, so part of the problem with computing the solution this way is we're infecting that correction with the conditioning of the original problem. So if the matrix is badly conditioned, then the correction is going to inherit, because we're using L and U, we're using the original matrix, the factorization, we're using the L and U, and that will infect the correction. So not only do we infect the solution, the initial value X, we're infecting the correction with the conditioning of the problem. Well, Nick and Aaron looked at this and says we can do better. We're not gonna use LNU in computing the correction. What we're gonna do is to use an iterative method. So we're gonna use GMRes. We're gonna precondition using LNU. So we have a pretty good preconditioner, but GMRes does not inherit the conditioning of the original matrix in computing its solution. It has some other problems associated with iterative methods in terms of convergence, but it doesn't infect the solution. So, so they showed that the method is better in some sense than using the LNU factors to compute a correction. Use GMRes. We're using an iterative method on a dense matrix. We have a good preconditioner. The preconditioner is the LNU, and we're going to use that to drive this iterative method. And in practice, it just takes a few iterations to converge. And again, we're not infecting the solution. So we end up with something which is a little bit better than we would had we done the solution the other way. So that was done, and Nick and Aaron have a very nice paper that talks about this and gives the error analysis. More recently, we looked at it and said, you know, we don't have to compute the correction. We're just going to use GMRes to compute the solution, not the correction, just compute the solution. So we have a good preconditioner. We have an approximation that we got from the lower precision results, and we're going to use that to start GMRes. And the solution there converges very rapidly as well, and we end up with a solution which is actually pretty good. So GMRes is used in this case here. So this is the algorithm that we settled on in looking at this problem, and we're quite happy with the results that we have for this. So let me just point out some of the details of of our implementation. So we're leveraging this half precision in the factorization. So the initial step says to factor the matrix using this half precision, 16-bit arithmetic. But we're really only going to use 16-bit arithmetic for doing the matrix multiplies. On the NVIDIA product, it's the 4x4 tensor core, which gives all the performance. So if you do anything that's not a matrix multiply, you're not going to get high performance. So we end up just doing the panel factorization. So in the LU factorization, there's a bunch of steps. The first step says to factor the panel. The panel's that this is this rectangular tall skinny matrix that we have at the kth step, having a panel that's that we have to do a LU factorization on. Then we do a triangular solve. We do some pivoting as well. And then we do a matrix multiply, where the matrix multiply takes part of the panel and part of the solution from the triangular solve and multiplies it into that green part of the matrix there. There's a sure complement to update that part of the matrix. So that's where the computational intense part is. That's where we're going to do 16-bit arithmetic in that matrix multiply. The factorization is going to be done in 32-bit arithmetic, and the triangular solve is going to be done in 32-bit arithmetic. Primarily because we're going to get better accuracy, and we're not going to get much enhancement because we don't do matrix multiply in those parts. The panel factorization is not driven by a matrix multiply, nor is the triangular solve. Although we can modify the triangular solve to get some matrix multiply, but we choose not to because it's a harder algorithm to implement. And at the time we did this, we didn't have all the pieces in place. So that's the algorithm that's being used in our implementation, and this is what it looks like on the tensor core. So what I'm showing you here is solving a system in 64-bit arithmetic. So the 64-bit arithmetic is the red line. That's the performance that we get. The purple line is to say factor the matrix in 32-bit arithmetic, and then refine the solution using the techniques I've talked about, using the GMRes part to enhance the solution. And you can see the numbers there reflect the number of iterations it took. So it's taking about 2 iterations to get to the same accuracy in the iteration part of the GMRes thing to get to the same accuracy we did had we computed the solution to 64-bit. So the single precision factorization is giving, when using this algorithm, using the refinement, giving the same accuracy as we got using the 64-bit. It takes 2 iterations, and you can see the time to solution here. It's reflected by the performance, since here we're looking at computing the rate of execution is just 2/3 n cubed operations over the time. It really is reflecting the time to solution. So we see a bump in terms of performance. And then the turquoise line here is doing a 16-bit factorization and then using the GMRes to enhance the solution. This is a well-conditioned problem. And in this case here, the iterations that it takes is only 3 iterations to enhance the performance to the same accuracy as we got with the 64-bit result. The conditioning of the problem is shown by this gray line here. So the gray line is this dotted line here. This is the conditioning that we have on the problem. The conditioning is 10 to the 5th is the worst condition, or roughly 10 to the 4th is the worst conditioning we're seeing on the problem. And we're still able to come to a solution which is pretty good in terms of the accuracy. So we're delighted by the solution, and this is part of the CUDA library today. So we get this factor of 3.5. This problem here is slightly worse in terms of the conditioning of the problem, in terms of the distribution of eigenvalues. It's causing us to take more iterations, but we still converge after 15 iterations. We're converging for a matrix of order 40,000 to the same accuracy we had in double precision, and we get an enhancement in terms of performance that's 3.5 times faster. So that's a big, and again, we're measuring time to solution here, not the number of operations. So even though it takes 15 iterations, I'm really reflecting the time to solution in this graph of the performance that we have. So it's a big win in terms of time to solution. This is looking at NVIDIA's new processor. So the results I've shown before were for the Volta, which is the last generation. The new generation, which was just announced, is something called Ampere. Ampere has some enhancements in it which allow it to run even faster. And what I'm showing here is differences between the solid and the dashed line. So this dashed line here is the results from Volta, and the solid line is the results from Ampere. So you can see the enhancement in performance that we see over that. So it's a significant, almost a factor of 2 enhancement in performance, both in double precision they've enhanced it, and also in the half precision results, big enhancement in terms of the performance that we see. So so that's something to look forward to in new experiments using the new GPU from NVIDIA. Okay, mixed precision. We're gonna achieve great things here exploiting lower precision to compute the computationally intense parts and then refine the solution. And now we're interested in how much energy do we save. So we're going to look at power consumption. We have tools which can measure power consumption. This is using our PAPI tools. And what we have here is a graph showing a matrix. This is a matrix problem that we're running. This is a large problem that we're solving, and we're looking at the energy that's consumed. So this is the power line. This is 64-bit results. This purple one is the 32-bit results, and the turquoise is the 16-bit results. So these are the iterative methods here. So this is the 64-bit results. Its performance is 5.3 teraflops. It's consuming close to 2,000 joules of energy, and the power is at 21 gigaflops per watt for this implementation. The same matrix using single precision is shown with this purple line here. So this is the energy consumed is this under the curve here. And this little bump here is the iterative refinement step. So this bump here is the solve part. So this is the factor and then the solve. This is the factorization is here. And then the iteration part and the solve part is this little bump here that we see in the purple part. And we got the same accuracy. We're achieving 10 teraflops. We consume 40 gigaflops per watt compared to 21. and the joules, the amount of energy is at 1,000 as opposed to 2,000. So it's about a factor of 2, which you would expect from going single to double. And then exploiting 64-bit arithmetic. Again, we get the same accuracy at the end of this as we did here. This is the iteration part again, this bump up that we see. And this is the factorization part. And the performance is at 21 compared to 5. So there's a factor of 4 there roughly. And the amount of gigaflops per watt is measured at 94. And the amount of energy consumed is at 460 joules. So again, we see this pretty striking power rating here of 94 gigaflops per watt, which is quite impressive for solving the system of equations. But that mainly is coming about because of the time to solution is reduced by such an amount. Okay, so that promoter, that gave us some pause and made us think about coming up with a benchmark for AI. And the benchmark that we have is something we call HPL AI. So we want to do a mixed precision benchmark here. So the benchmark is trying to exploit that precision, that difference in performance between 16-bit and 64-bit, and trying to do it using this iterative algorithm. So the benchmark uses the factorization, the lower precision factorization, uses iterative refinement using GMRes, and computes the same accuracy as we got had we done the whole computation in 64-bit arithmetic. And it uses this algorithm here. So factor the matrix in lower precision, compute a solution, and then use GMRes to do that. And if you're interested, there's a website which contains more information about this and gives an implementation and talks about this in greater detail. So here's the results on 2 machines. So these are the 2 fastest machines that we have. The Fugaku machine, which was just announced a couple weeks ago at the ISC meeting. So it is the fastest computer. What I'm showing you here is the name of the machine, where it is, the number of cores that it has 7 million cores. These are ARM processors. It achieved this performance on LINPACK. So this is the HPL. This is 64-bit, straight 64-bit, no mixed precision. So 0.4 exaflops is what it achieves. And it ranked #1. And when we run this new benchmark, the HPL AI, it achieved 1.4 exaflops. So it achieved the same accuracy as if we had done everything in 64 bits, but it uses 16-bit factorization, exploiting the hardware in the ARM processor that Fugaku has for 16-bit floating point arithmetic, and achieves a speed up of 3.4 over what we got with the HPL results. And then Summit, which is #2 now on the top 500 list, which exploits NVIDIA's Volta processor. It has with my count, oh geez, I'm going the wrong way. That's not what I want. So let's go, whoops, I'm sorry. I'm getting confused here. I don't have a mouse. My mouse controls are not quite as good as I'm used to. There we go. Okay, so the Oak Ridge machine is #2 today. With LINPACK benchmark, it achieved 0.14 or 144 petaflops. And with the HPL benchmark, it achieved half an exaflop, which is about 3.8 times faster than it had. So I guess one thing that I want to point out is that Fugaku does not have a GPU. It's a conventional architecture. Think of it as a vector architecture. So you can put vectors in and do vector operations, and those vectors extend 64-bit, 32-bit, and 16-bit kind of things. And using the 16-bit arithmetic, we can get these. We can exploit this higher precision, and that's an interesting results that we have, and they'll be exploited in the future. Okay, so let's go to conclusions here. I guess I'm running out of time. We can accelerate the solution to solving systems of equations using 16-bit floating point arithmetic that's available on GPUs and also on some conventional processors. We introduce a framework for doing this. We do this iterative refinement. This can be done for all the factorizations, LU, Cholesky, symmetric indefinite, and also for QR. It can also be done for for double-sided factorizations, eigenvalues and singular values. It typically pays off when you want to do just a few. And we're working on an implementation today which exploits this on the NVIDIA and also on Fugaku architectures for the eigenvalues. Our techniques show that you can, the number of problems can be accelerated. You get 4 times speed up using these tensor cores over what we did with 64-bit, and you can also get this factor of 2. And you get this energy enhancement as well, but it's mainly coming because we're solving the system in faster time to solution, I guess is the right way to say that. And we illustrate these techniques on the NVIDIA and Volta. And there's an error analysis that supports all this so that it works. Again, there's these caveats about the conditioning of the problem. If it's too badly conditioned, it's not going to work. And you also need a copy of the original matrix to do the residual. So it's very critical that you have the original data in computing that residual. Otherwise, the method won't work at all. So that's really what I wanted to say. I guess I can take my mask off at this point. Everybody must have guessed who I am, I hope. So there you have it. This is joint work with myself, Azam Hajar from NVIDIA, Nick Hyam, and Stan from my group. So there you go. Thanks for your attention. And I guess I'm happy to answer any questions.
Great. Thank you so much. Thanks, Jack, for being our guest speaker today. So if there are any questions, I mean, you can go ahead and unmute and ask your question.
May I?
Yeah, please.
Oh, David. Hello, David.
Hi, Jack. Thank you for that very fast-paced, enthusiastic talk. It's even so much further than the November talk that you gave at our booth last year. Very exciting. Your enthusiasm reminds me of a teenager chasing fire trucks, which is some people at our age shouldn't be doing. But based on the way every new architectural feature has a new twist for you to exploit, let's put the thing in reverse. I remember about 10 years ago, you and I were at a meeting where Bill Dowley said, "Tell me one change you can make that costs me only 10% the cost of a GPU, but makes me sell 10,000 copies to scientific computing." And so I would like to pose that question again. The matrix, the 4x4 matrix multiply has opened a huge gate, but it doesn't substitute, for instance, for the panel factorization or other, features. And maybe there's data motion that gets in the way or whatever. What would be the next one thing that you would request of a chip designer that could open, that could get past the next bottleneck, not necessarily the n-cubed one, but maybe something else?
Right. So when we look at the bottlenecks, well, the floating point performance is clearly one, but let's say we solve that with the hardware solution here. It's not quite solved, but it's been enhanced so that we have a better way of doing it. The next thing, and maybe it's even more important than the floating point, is data motion. So if we could enhance the performance of data motion, that is speed it up in some way. I'm not sure it's going to cost just 10%. That's the other catch is that it's not a cheap solution to the problem. We might be able to do better. If you take a look at Fugaku is a very well balanced architecture. So it was designed to do computational science problems. It's perhaps not surprising that it is more balanced because of that. It wasn't designed to be in PCs, to play games, to do other things. It was really designed for high performance computing. And they paid attention to that. So the memory is all stacked memory. There is no, there is of course caches. So there's a hierarchy, but the hierarchy is in some sense enhanced because they have very fast memory associated with it. So data motion is costing less than it does on more what I'll call conventional architectures. Of course, they have a network which ties together all the processors, which is also very fast. So those are the things which I think can enhance the performance even beyond what we have today. And Fugaku is an example where they've done that. That machine is not cheap. So again, I'm not sure it's a 10% solution to the problem. The cost, I believe, Satoshi Matsuoka is claimed to be $1 billion US. So that's a very expensive piece of equipment that they have. And it is the fastest computer. Yeah, I think it pushes the technology. It's simpler to use than what we have. What we have with Summit, with a GPU-based system, is basically we're in a situation where we have to write two programs. We have to write a program that runs on the host, and then we have to write a program which runs on the accelerator part, and that causes some stress in terms of developing things. If we think about our time to develop and our time to solution is not enhanced because of that obstacle that's put in the way. It makes debugging more difficult. With Fugaku, they don't have that. So they have a vector architecture, more conventional. You have to develop one program, not two, and it allows things to I think proceed more quickly. So I would say the user time to solution is going to be enhanced with that architecture. So you pay a price one way or the other. But yeah, so again, if I had one thing to choose, I would choose DataMotion.
Okay. Maybe you'll help us with our Shaheen 3 that way, with that advice.
So you can buy the, so we're getting a machine at Oak Ridge, which is going to be based on the ARM processor that's in Fugaku from Cray. So Cray is marketing a product that has that processor.
Great. Thank you.
Great. Any other question? So Jack, I had a question. We have a few students listening here, and yes. Mixed precision, it seems to be a hot topic these days, right? And you had that single line at the end of your conclusion, which of course has lots of weight when it comes to making sure not only you compute fast, but you have an error which is, okay, right? So that has lots of weight, your last statement. So for those students, I mean, when they listen to mixed precision and see the performance improvement, they really see stars in their eyes, and they're really excited about it, right? But how can they exploit it? How can you comment on how can they basically identify maybe section in their code or in their application? Let's say they work with application scientists, for instance. How can they identify those sections that could be resilient to computing in lower precision? Are there tools out there to do that? Automatic detection, for instance, or yeah. Can you comment on this?
Right. So that avenue has been looked at. So my colleague Jim Demmel is writing something, or has some ideas about tools which will analyze a program, make some determination about the numerical accuracy that can be extracted, and make decisions about how to pinpoint places within the application which are computationally intense and may benefit from exploiting lower precision. I don't know how far along that work has gone. It sounds quite exciting, to be honest. And if you could do that in a way that could be automatically applied to a program by a pre-processor to a compiler, that would be a great enhancement to numerical computations. I think it's something that should be pursued. So I would encourage people to look at that, and we'll see how realistic or how relevant that can be made for computations in general. But I think there is something there, and it would be good to look into it.
Very good.
So just for the students who are here, or maybe that could be passed along. In my group in Tennessee, we're always looking for good people, and we're always looking to enhance our group, our team, with additional people who can join us and make things work a little bit better. So we hope that we can encourage people to join us. In the U.S., we have a rather awkward situation at the moment because of the political climate, but I would assume that that's going to relieve itself come November. There's no promises there, but that could be a wish more than anything else.
Great. Okay. Any other question for Jack? I may have maybe a last one or another one. So you mentioned how data movement is critical, right? So people have been looking into compression, right? Compression to, think of, for instance, Frank Capello work, compress the data and then move that data which is compressed and, hopefully save some latency and get high bandwidth there. Do you see, how can this be also, leveraged and used in scientific computing? Do you see also a tool there or, yeah?
Yeah, so there's you're right. So that's another great area to explore. I would say there's still unanswered questions. People are looking into it, looking into that idea about doing data compression and do it perhaps selectively on the data. So instead of the whole data being compressed, look at blocks and do the compression on the blocks and do that in some way that makes sense. There's been some papers written about that. And again, I think the results look promising. The other thing that people are starting to look at is use integer arithmetic. So in some sense, look at fixed point arithmetic using integers. So integers run very fast on these machines as well. I didn't point that out, but I should have perhaps had a slide which talks about the enhancement that can be made there. So think about converting the floating point to integer, do the integer arithmetic and fixed point, and then convert back in the end, and exploiting that high performance that you can gain from the integer arithmetic. And Fugaku, I think, goes down to 4-bit integers. I don't know if you can get away with that, but if you can, there's another thing to exploit. So there's a paper that we're writing which talks about mixed precision in a general setting. This is coming out of the DOE ECP efforts. There's a lot of people in that group of who are looking at this. And we're about to have a working note or to have a paper which talks about this in some detail and looks at various things. I think compression is included, integer arithmetic, looking at dense and sparse computations, I think get thrown into the mix as well. So it tries to do an analysis of how mixed precision could be exploited across all of those areas.
Very good.
I have a quick question.
I think Bill,
yes. Yeah. Thank you, Jack, for this nice talk. Regarding the implementation with the GMRS for the mixed precision on the GPUs, is it the same algorithms also that is now implemented also for the CPU, or now it's too different? So if a user...
it's the same algorithm, yeah. So we're promoting one algorithm and then doing an implementation that's done for the GPU or for the CPU. I think that's the right way to go.
Okay.
Just in truth and advertising, it's a flexible GMRes that we're using. In the details of that, I think we have a paper which talks about that. I think the paper's under review right now, which talks about the specific details about the flexible GMRes that's being used in the method itself. And there's some reasons for doing that, and it goes into it in detail in the paper. So that's out there somewhere.
Excellent. Thank you.
Jack, you've planted many ideas this morning, and we'll plant one back that might be useful pertaining to data motion. On July 9th, one of the students listening is going to defend his thesis on something called a multi-layer buffer system, which is a generalization to 3 or more levels of memory hierarchy of a traditional 2-level prefetch kind of a idea. And uses the obvious architectural feature. We have a lot of extra cores now, so the CPU doesn't have to be encumbered by managing the memory motion. And perhaps this is something that right now it's being mainly used for disk with seismic inversion, because that can be more than half the compute time, makes it go away. But maybe it can also be used on the data path within these other differential levels of memory bandwidth, within a processor. So we'll keep an eye on that, and hopefully look at that next bottleneck with you.
Sounds good. Sounds like a good research direction to go in. That's a good idea.
All right. Just to I guess. Oh, Yushi, you have a question?
Yeah. Thanks for the very inspiring lecture. And since Hatton mentioned the compression and you mentioned the fixed point arithmetic, so I'm really glad that you mentioned this, because currently I'm working on the compression. I'm also thinking about the fixed point arithmetic, but I came across a problem that the fixed point arithmetic is a very small range of the numbers, because it with 32 bit you can only have a range maybe from, it depends on how you choose the decimals, and but have you think about that problem?
Yeah, well, so it's you have to do scaling, of course, and then you suffer underflow or overflow issues when you start manipulating things, and so it does confine things. So you got to be very careful. It's not a solution that can be applied blindly. It has to have some way to confine things, or to know when you're going to run into trouble. So I would say it's something that needs to be looked into, and the boundaries defined in a more precise way. Right now, it's intriguing because of the performance enhancements, but we need to really understand what those boundaries are, where it can be exploited. And again, it's an issue of scaling and controlling underflow and overflow associated with it. Okay. But I think it's a good thing to pursue.
Thank you.
So David, what's your background there? It looks very English. You're muted. You're on mute, David. David, you're muted.
This is the main street of Portsmouth, New Hampshire.
New Hampshire.
My wife retired at the end of March. We finally got a flight home on June 29th.
I see. Very good.
I think we're going from the frying pan into the fire in terms of the pandemic. However, New Hampshire is, I think, the third most effective state now, after Hawaii and Vermont, in staying in controlling the virus. So hopefully we can last here a little bit longer until I come back for new student orientation in mid-August.
I see. Okay.
But meanwhile, we're in the same time zone.
I see. Oh, very good. I didn't realize you were back at least temporarily. So just the picture that I have as my background.
I love it. I adore it.
Tell us the story, Jack.
I'm the image on the I'm the guy on the first camel, and my wife is on the second camel.
No kidding.
So, that's right. so that was taken in Morocco. We took a vacation in Morocco a few years ago. So that was the image at sunset as we're having a camel ride back to the camp, which was really good.
That is so great. I just swapped in the Portsmouth waterfront, being a tourist promoter.
That's right.
You know, it's a city that's only an hour from Boston, but it's got beaches, and I can walk to Maine in 10 minutes. So.
Wow, I see. That's nice. Yeah, I was going to say the picture looked like someplace in England, but I guess New England.
Well, it's named after Portsmouth, England. It was established in 1630, so just 10 years after Plymouth plantation.
Yeah, I was reminded of Manchester when I saw the picture. I could be in Manchester now, but obviously I'm not.
Absolutely, yeah. We were supposed to be there for your birthday in about 2 weeks. Yeah.
That's right, exactly. Next year.
Right. Everything is next year.
Everything is next year. That's exactly right.
All right, great. Let's thank Jack again, I guess. And
thank you very much for the invitation. It was really fun.
Great. Thank you so much.
Great.
Cheers. See you next time. Bye-bye.
Bye-bye.